Good morning. This is a talk about the Gaia Space Telescope. As you can see from the sort of subtitle at the top, it had a 5-year mission to map 1 billion stars within the Milky Way. It worked really well, so they very quickly changed it to a 10-year mission to map 2 billion stars in the Milky Way. So what I'm going to be talking about this morning is why we map the Milky Way, how it can be done, what type of data we might get, and what can we learn in terms of, astronomically speaking, what do we learn about how the Milky Way has evolved and changed over the billions of years. So you could start with, well, basically, why do we map the stars? If you get a star atlas, whether it's a paper atlas or an app on your phone, you can see where the stars are. But it's not simply a question of saying, well, we want to generate a map of the sky so that we can basically find where the stars are if we want to find them tomorrow, or tell if something has moved, or to tell if any new objects have appeared. That, you could argue, is a very mundane reason for making a map of the sky. In the case of Gaia, the main aim was to make a full 3-dimensional map of where the stars are, not simply where they appear to be in the sky, but their position in the sky as well as their distance, so with a 3-dimensional picture made explicitly at very high precision, we will then be able to gain a better understanding of how stars have evolved in the Milky Way, and also how the Milky Way itself as a galaxy has changed its structure, the dynamics, and the history of the Milky Way galaxy. So how do we map the sky? You could say, well, don't we just take a lot of pictures and then stitch them together? That idea, of course, works for the Earth. We just take lots of pictures, stitch them together. We've got a picture of a map of the Earth. But one of the problems is stars move. Nothing in the galaxy is actually static. And a second problem is it's not simply a question of taking a whole load of 2-dimensional pictures, because stars are at different distances and 2-dimensional mapping is not good enough. So for instance, if we think about the constellation Orion that we see on Earth, Orion makes a particular pattern in our night sky, but all the stars of Orion are actually at different distances. And so if we were to look at those stars from a slightly different perspective, we would see, of course, completely different patterns. We need to know their distances to know exactly how the Milky Way is behaving as a dynamic structure containing many billions of stars. So being able to determine the distance is not only important for understanding 3-dimensional structure, it's actually important for understanding the stars themselves. If we look at the map here, which is the standard way of mapping out stars, the vertical axis is luminosity and the horizontal axis is either surface temperature or color, if you prefer. We can see that in this particular case, if we don't know the distance to a star, then we don't know whether we're looking at a bright star that's very far away or a dim star that's very close. So if we don't know distances, we actually don't know luminosities. And so, for instance, if we were interested in a star with that particular temperature, that particular color, we wouldn't be able to tell whether it was a supergiant or a main sequence star or a white dwarf. And similarly, if we looked at a red star without knowing its luminosity, we wouldn't know whether we were looking at a supergiant or a red giant or a red dwarf. So we absolutely need to know distances in order to know luminosities, in order to know what type of star we're looking at. Yes, you can get clues from the spectrum of a star, but ultimately we really want to know the distance. And without knowing the type of star that we're looking at, well, actually, we don't get much information about exoplanets either. That's a somewhat side issue. But quite often, exoplanets are characterized by what is their size relative to their host star? What is their mass relative to their host star? So if we don't know the properties of the stars, then we really don't know much about the properties of any exoplanets that might exist around those stars. So understanding distance is important for multiple reasons. Knowing the 3-dimensional structure of the Milky Way, as well as understanding stellar evolution better than we do now. So in order to get at distance, what's the standard way of measuring distance to the stars? It's a system called parallax. Parallax is basically talking about the motion, the apparent change of a position of an object in the sky due to the motion of the Earth around the Sun. So we know we're 150 million kilometers from the sun, and of course every year we go around the sun, which means a close-by object will appear to move relative to more distant objects. The standard way of thinking about that is the usual hold your finger up and look at your finger with both eyes. You see your finger jump against a backdrop of more distant objects. But a diagram like this that says, well, when the Earth is at different points in its orbit, a nearby star will appear to move relative to more distant stars. These sort of cartoons are always oversimplified because it always assumes that a nearby object will move relative to some fixed background object to determine the parallax. And the parallax we're after is that very small angle there. Remember, the distance from the Earth to the sun is quite a few million kilometers, but the distance to most stars is hundreds or thousands of light years. So the actual angles involved are absolutely tiny. In practice, we haven't got this situation because although in principle we look at the movement of nearby objects relative to more distant objects, every star in the galaxy appears to move and every star in the galaxy is actually moving. It's partly the fact that the Earth is moving, so our perspective is changing, and it's partly the fact that the stars themselves are actually moving around the Milky Way. So we've got multiple movements that we have to try and disentangle, not helped by the fact that these angles are very small. A star that's 3 light years distance, for instance, would show a parallax angle of 1 arc second. Remember, 1 arc second is 1/60th of an arc minute, which is 1/60th of a degree, which is something like 1/60th of a radian. So even relatively close stars have parallax angles which are quite tiny. The distance at which an object would have a parallax of 1 second is called, not surprisingly perhaps, a parallax second, or it's been abbreviated to a parsec. So 1 parsec is the distance at which an object would have a parallax of 1 arc second. In fact, there are no stars closer than 1 parsec. 1 parsec is 3 light years. The closest star is about 4 light years. And we're interested in mapping stars not 4 light years away or 10 light years away, but we want to be able to stretch to hundreds or thousands of light years. So we're talking about smaller and smaller angles. The greater that distance for a given baseline, the smaller these angles become. So Gaia is all about the precision with which we can measure tiny movements of stars on the night sky. So there's the crux of the problem. We need distances for the reasons I've explained. So we need parallax. Parallax needs the motion of a star as the Earth goes around the sun, and we need the actual position of the star, not the position of a star relative to another star that happens to be nearby, because if all the stars are moving, we can't use relative motion to tell us whether that star is moving the way we think it is because of the motion of the Earth around the sun. So relative positions aren't good enough. The stars themselves are moving as well as the change in perspective of the Earth's motion. We call that motion proper motion, the actual motion of the star around the Milky Way. So that ultimately is why mapping the stars in the Milky Way is not a trivial task, and that's why it hasn't been done to this level of precision until relatively recently. So how can the stars be mapped accurately? If we have a sort of cartoon version of what we think is actually happening, if we look at a random collection of stars in this simulation, each of these stars is moving, apparently, because the Earth is moving around the sun, and it might be that some of these stars have their own motion as well. So it's a little easier to see if I just draw some arbitrary circles. Those are just imaginary circles in the sky, and you can see that individual stars could be moving a little bit or a lot relative to their neighbors. But how are you going to disentangle if one star is moving relative to another? Which is the star that's actually moving? We need a coordinate system that is absolutely fixed. How can we tell which stars are apparently moving because of the Earth and which stars are actually moving around the Milky Way? That is the crux. And untangling the apparent motion because of parallax and the actual motion because of Milky Way dynamics, that is a real technical challenge. So we need high precision. Well, perhaps I should say ultra high precision. We need phenomenal precision in order to make good measurements of the stars to disentangle, is the star moving, or is that because of the Earth's motion around the sun, which we can then use to get its distance. And we need a fixed coordinate system because relative coordinates simply are not good enough. Parallax angles are very small. Remember, 1 arcsecond is for the very closest objects. Most distant objects will be a tiny, tiny fraction of an arcsecond. And we need a fixed coordinate system because both the Earth and the stars are in motion. We know how the Earth is moving. If we want to know how the stars are moving, we've got to disentangle these various things, untangle these various effects. Just as an aside, there were thoughts some years ago of saying rather than use the baseline of the distance from the Earth to the Sun and take measurements in June and July for a given object, why not take a baseline of a telescope a long way from the Sun? So there were plans to move an object, not 1 astronomical unit from the Sun, which is where we are on Earth. Why don't we fly an object 1,000 astronomical units away? This is way beyond, for instance, how far Voyager has so far reached. So it would have taken decades to get a telescope out to the outer solar system, but it would have given us a much longer baseline, making it easier to measure angles in principle. But that never flew, if you'll excuse the pun, for various reasons. The technological challenges of doing that, as well as the timeline of spending 50 years to get it in station, would have been problematic. So what coordinate system do we want to use to map the sky? Mostly, when you buy a star atlas or look on your phone at where are the stars, what's the coordinates of this star, we use a system that's analogous to the longitude and latitude of the Earth. A position in the sky would be measured by right ascension, which is analogous to longitude, and declination, analogous to latitude. In other words, the coordinates are relative to coordinates that are defined by the Earth. The Earth's equator defines the celestial equator, and we take measurements north or south of that imaginary line. Right ascension and declination have been used in star atlases since the days of the first Astronomer Royal, centuries ago. So why is that not good enough for Gaia? If we think about, again, a star atlas, here's a load of stars that are plotted, and we have grid lines that tell us the right ascension and declination values. So in principle, we can just read off the coordinates of a star by reading off the coordinates in right ascension and declination. The reason that's not good enough is because these coordinates change. If we have a look at a star atlas, not the print dates here, it's the epoch dates, it's the dates at which the coordinates of the stars were defined. So many decades ago, the star atlases were printed with these are the coordinates of the star as defined on the 1st of January 1950. More recently, we have star atlases defined for these are the coordinates of the star defined for the 1st of January 2000. Why do the stars change their coordinates? Is it because the stars have moved? Well, not necessarily. It could simply be because the Earth's axis precesses. And it might not precess much from year to year, but over decades it will change, and all the stars will appear to change their coordinates simply because the Earth's equator is no longer in the same place, because the Earth's pole is now pointing to a different part of the sky. So if the Earth continually precesses, that means right ascension and declination will change. In principle, second by second by second, right ascension and declination coordinates keep changing, regardless of whether the star is moving or not. So Earth-based coordinates are not good. Okay, so if you can't use Earth-based coordinates, why not take the Sun as a reference? That might seem more logical, but even that would lead to small errors because the Sun does actually move in the solar system. If we think of where the Sun is, this particular animation is simply slowing down so we can see it a little more clearly. The Sun moves around the center of mass of the solar system. It's relatively close to the Sun, the center of mass, because the only other objects that are anywhere close to the same mass as the Sun are the relatively small planets like Jupiter and Saturn, etc. Very large for planets, but of course not particularly large compared to the Sun. So the Barry center, the center of mass of the solar system, is relatively close to the Sun, but it isn't necessarily at the center of the Sun, and sometimes it's inside the Sun, sometimes it's outside the Sun. So the only thing that we really ought to care about is the center of mass of the solar system. And then we can work out where the stars are relative to that fixed point, regardless of what the sun is doing and regardless of what the Earth is doing. And we can calculate that as long as we know where all the planets are, etc. And we do reasonably know all of those parameters. So the best coordinate system to use uses the center of the solar system as a fixed reference point. If we find that fixed reference point is actually moving, it's because the solar system is going around the Milky Way, which is precisely what we want to know. How is the solar system moving through the galaxy, as well as how are all these other stars moving through the galaxy? So we've got the coordinates sorted as long as we are careful about which coordinates we're going to pick. And we also ideally need some fixed points in the sky that tell us that point is unmoving. In other words, that point is so far away, the motion of the Earth around the sun or the motion of the sun around the barycenter, none of these are going to make any difference to the apparent position of that object. In other words, we choose not a distant star, thousands of light years away, we choose a very distant galaxy. Gaia is mapping stars, and by accident it maps galaxies as well. Some of those galaxies are on the other side of the observable universe. They are so far away, the motion of the Earth can't possibly make any difference to those objects, and therefore they can act as fixed reference points. So quasars, very distant galaxies, give us a fixed set of points relative to the barycenter of the solar system. If we were to only look at parallax and think about what the sky would look like if that was the only thing we were interested in, then the sky would look like this. Every star in the sky would be going round in a circle, depending on which part of sky we're looking at. The very close objects would move in big circles. The very distant objects would apparently move in very small circles as the Earth goes round the sun. If we take into account the fact that all stars are moving as well, then we have parallax as well as proper motion. So we have circular motion because the Earth is in motion, and it might be that stars themselves are in motion throughout the Milky Way. So when we superpose circular motion because of Earth going around the sun with the fact that stars might be moving, here we've just assumed that they're moving in straight lines. Strictly speaking, they're moving around the center of the Milky Way, but over a few years they are effectively moving in straight lines through the sky. So what we actually see for the motion of stars is circular motion superposed on linear motion, so effectively all the stars in the sky will be corkscrewing very slowly. We don't ever notice it when we're looking through a telescope. Amateurs don't notice it because the effects are so tiny. But Gaia is trying to measure the plot of all of these star motions to disentangle what is parallax, what is actual motion around the Milky Way, to give us the dynamics as well as the distance to these various objects. The first satellite that attempted to do this was called Hipparchus. I think this is a question of a backronym. They decided that they wanted a satellite that came out to sound a bit like Hipparchus, who's the founder of trigonometry, and they came up with this particular name, High Precision Parallax Collecting Satellite. Built in the 1980s and operational in the 1990s, Hipparchus's job was basically to map the positions of stars as accurately as possible for the 1980s, and that produced star catalogues. It produced positions of hundreds of thousands of stars with an accuracy of order 1/1000th of an arc second, 1 milli-arc second. Remember how small an arc second is in the first place. Here we've got precision of milli-arc seconds. And the Hipparchus catalogue that was generated by the Hipparchus satellite, that was used for decades as a standard. For instance, it was used by the Hubble Space Telescope so that the Hubble knew exactly where the stars were in terms of their coordinates. So if it was tasked with find this galaxy or take an image of that nebula, it knew precisely where to point with fantastic accuracy. So the Hipparchus catalogue was very valuable. But 20 years later, it was decided, yes, Hipparchus was fantastic, but we need higher precision. Hipparchus only maps 100,000 stars. That's quite a lot of stars, but it is a tiny fraction of all the stars in the galaxy. And it only goes down to that sort of level of accuracy. milliarc second, which only gets us to hundreds of light years. It would be really good if we could get better accuracy, which gives us better reach because we can go further into the galaxy and see tiny changes in more distant stars, and hence we get a better sampling of all the stars in the galaxy. So that's why Gaia was put together. Gaia was originally that global astrometric interferometer for astrophysics, a really awkward acronym. But after a little while, they decided, no, let's not use an interferometer. We found a better way of doing it. So although that was the original name, and that was the original concept on the drawing board back in the noughties, it was started around the turn of the century, they decided that although that's a nice name, we're not going to use interferometers, but what the hell, let's keep the name anyway. So they kept the name Gaia, even though they decided not to use interferometric techniques. Gaia's mission was to improve on Hipparchus by mapping not 100,000 stars, but nominally 1 billion stars, and not with milliarc second precision, but with tens of microarc second precision. So now we're talking about really silly numbers in terms of the precision with which Gaia was tasked to measure the positions of stars. Higher precision means we can see movements of stars at a much greater distance, and so we have a much greater reach into the Milky Way, and hopefully we can sample a lot more stars in the Milky Way. An analogy, because if I keep talking about arc seconds, it's going to mean nothing in terms of, yes, it's very precise, but just how precise is a milliarc second or a microarc second? Generally speaking, it's only astronomers that work with those stupid units. Physicists tend to work in radians or microradians or nanoradians or picoradians. But in a fraction of an arc second, it's difficult to judge what it is we're talking about. So the nominal precision of Gaia is something of order 10 microarc seconds, or that number of arc seconds if you prefer. That is equivalent to measuring something with the precision of the width of a human hair at a distance of 1,000 kilometers. So if you imagine it, if you were standing in Land's End looking at somebody in John O'Groats, if they held up a human hair, you could tell whether or not they moved it 1 human hair width to the left or 1 human hair width to the right. The precision of a human hair at that distance is absolutely mind-boggling, and you can understand the achievement in terms of the design and the technology and the engineers of putting something together which is capable of measuring stars to that sort of ridiculous angular precision. Before I talk about the details of Gaia, you might say, well, okay, they want to produce a map of the stars, but why did they decide to build Gaia rather than use another telescope that already existed? For instance, we've got lots of great telescopes around. For instance, we've got the Hubble Space Telescope, which has fantastic resolution. And now, relatively recently, we have the Chamonix Survey Telescope working in the Vera Rubin Observatory, that also known as the Large Synoptic Survey Telescope, carrying out the legacy survey of space and time. Weren't either of these instruments capable of doing the job that ultimately they gave to Gaia? If we think about the precision and the number of stars that could possibly be covered by these telescopes, well, Hubble has almost the same precision. It can certainly do better than milliarc seconds, not quite as good as Gaia, but it's certainly fantastic. And the Chamonix telescope can certainly cover billions of stars. That is what it's going to be doing for the next 10 years, is surveying the brightness and colors and positions of more than 1 billion stars. But unfortunately, one has the precision and one has the speed at covering lots of stars. The Chamonix telescope hasn't got the precision. At best, it could do a fraction of an arc second, let's say 100 milliarc seconds. And the Hubble has been looking at the positions of stars, but it's only dealt with something like 1,000 stars or so. So although the Chamonix telescope could cover billions of stars in its lifetime of 10 years, if you asked Hubble to do the same thing, it would be capable of doing the same measurements, but it would take about 1,000 years to do it. And that's looking at every star once. Ideally, you want to look at every star 10 times or 100 times and start averaging your results. So Hubble could do it, but it might take 10 to 100,000 years to actually do it. That was considered a bit long. The gyros could fail in a few years. They certainly won't last for centuries. So no, there is no telescope around that could possibly do the job that they eventually tasked to Gaia. So how does Gaia achieve the phenomenal precision of measurement over many billions of stars? When I put this talk together, I thought it'd be interesting to talk about what Gaia can do in terms of how we interpret Gaia data and how we learn about the Milky Way. But then I started thinking, well, actually, the internal guts of Gaia are almost more interesting than what it is we're actually doing with the data. So I thought I'd spend a few minutes talking about how it actually works. Gaia is an ESA project. It's a European project. Various companies around Europe have collaborated to produce the hardware. So, for instance, the optics were built in Germany and France and Belgium. The detector was built in the UK. Hurrah. Yeah. And some of the electrical systems were put together in the UK as well. So Astrium was the organization that ultimately pulled everything together by taking components built in various partner countries, and then it was all taken to Toulouse and put together by the company called Astrium, which has now been redefined as part of Airbus. So effectively, this is genuinely a European collaboration now under the Airbus banner. Gaia was constructed. It was planned about 2000. It was constructed 2006 to 2012. It was launched on a Soyuz rocket from French Guiana in December 2013 and placed in a halo orbit around L2 in January of 2014. L2 is the now familiar point where James Webb is also sitting. If we ignore the other Lagrange points, L2 is sitting there 1 million miles above the midnight point of Earth. It's in a small halo orbit like the James Webb and other satellites. And because it has a sun shield there, that much like the James Webb, that sun shield can block the light of the sun and the Earth and the moon, which gives Gaia an unreserved view of the sky, which during the course of a year, it can map the entire sky multiple times. This is what it actually looks like when it was being put together, and there's the sun shield being deployed. You get an idea of the size, about 10 meters or so diameter of the sun shield. Solar panels on the underneath of the sun shield gives it the power. Everything else is kept nice and cool on the other side of the sun shield and no stray light getting in. So of course they double checked the deployment of the sun shield multiple times to make sure everything was okay. Coming back to the deployment, okay, we've got it to L2, it's in orbit. How does it actually achieve micro arc-second precision? You could argue that large mirrors give you high angular precision through diffraction effects. So do you need mirrors that are substantially bigger than the Hubble? If you want a precision 100 times better than Hubble, do you need a mirror 100 times bigger? Not quite a few meters, but a few kilometers. Well, obviously not, because we know the size of Gaia is only a few meters in diameter. So how, with mirrors only a few meters in size, do you possibly get that level of precision? A reminder about how big telescope mirrors have evolved, not since Galileo's time, but just over the last 100 years or so. The largest telescope in existence at the moment has a 10-meter diameter mirror. Diameter is taken rather loosely because they are hexagonal segments, but that's the 10-meter diameter Gran Telescopio Canarias on the Canary Islands. Down in the bottom left, we have all of the space telescopes that you might have heard of. So there they are. Let me make those a bit bigger so you can see them more clearly. There's the James Webb and the familiar Hubble, but you notice that Gaia's mirrors are not circular, not hexagonal. There are two telescopes in Gaia, and they both have rectangular mirrors. But they are no bigger, nominally, than the Hubble, and yet they can achieve phenomenal positional accuracy with the precision at which they can measure. And that's through an ingenious combination of instrumental hardware and how they use that hardware, the novel mode of operating. So that's worth taking a look at how it works. A large CCD array was built in the UK at a company called E2V, English Electric Valves. It's a gigapixel detector made up of about 100 individual CCD sensors, or CCD modules, if you like. And Gaia has 2 telescopes pointing in different parts of the sky. If you think about the idea of, well, you could in principle work out where the stars are by working out where that star is relative to its neighbour, and then that star relative to its neighbour, and that star relative to its neighbour, and working around the whole sky. But of course, errors will add up. And even if the errors are small, by the time you've done that 1,000,000 times, you will find that your errors are amplified. So the idea is you look at stars simultaneously in different chunks of sky. So at worst, you're working out the error between a star position there and a star position on a different chunk of sky. If you do that repeatedly, you can cover the sky without compounding all of the errors of individual measurements. The operation is the interesting bit. There are 2 telescopes, but they generate images on the same detector, which when I first read that, I thought, that can't be right. Surely one telescope produces images on one detector and another telescope produces images on a second detector, and then somehow they compare the 2. No, the 2 telescopes are actually producing stars on the same detector. Gaia is continuously spinning, and so the stars are always drifting across the CCDs. The bottom line is Gaia does not take images. Yes, it's a space telescope, but it is not taking images in the same way that Hubble or the James Webb Space Telescope take images. It is a very different mode of operation. And the way the data is read from the CCDs is crucial to the way Gaia works. So it's worth taking a closer look at. Okay, light is falling on a CCD. A CCD is a charge-coupled device. The light is converted into charge, and we want to measure how much charge has been made to work out how much light has been generated by this star. And in the case of Gaia, it is absolutely central to the problem of how do we get charge from a CCD device or collection of CCDs? How do we convert that into data in terms of ultimately star positions? Firstly, it's worth reminding ourselves, how does every other telescope work? Regardless of whether it's a telescope like let's say the Hubble and the James Webb for the sake of example, but there are other telescopes that work in the same way. If you take a CCD sensor as a camera, the way they normally work, the same for ground-based telescopes as well as space telescopes, is basically you stare at a patch of sky and you expose. And after you've exposed, which could take a second or a minute or an hour, depending on what light you want to capture, after you've exposed the CCD to the scene you're interested in, then you read out the data. So you can imagine if you have a patch of sky, one thing you have to remember is that ultimately an image is just a collection of numbers. You think of it as an image, you think of it as something visually, but ultimately it is only a collection of numbers. So let's see how that works. Normally, you expose a CCD to a patch of sky and the image builds up and builds up and builds up and builds up over seconds or minutes or hours. Once the exposure is complete, then you get this process of the charge moving from one row to the next and then shuffled along in a register, and each individual pixel has the charge measured and converted into digital data. Then the next row shuffles down, and again the register shuffles across, and each pixel is read out individually. It might take a millisecond or so to move all the charge from one row of the CCD to the next, because remember, we're usually dealing with millions of pixels. It might take a millisecond to shuffle down, but then it takes something like a microsecond to read one pixel, and then the next, and then the next, and then the next. When we are finally done, we have read all of the charge from the CCD, and we've converted all of the information about the charge in each pixel, which is related to the amount of light that hit each pixel. We've now converted all of that to a set of data. That is how things work when you simply stare at a patch of sky and then when you're done, read the data out. Sometimes that's called stare mode for imaging. Gaia doesn't do that. Gaia works in drift mode. In Gaia, remember, it's spinning continuously. It takes about 6 hours to spin once, which means the star field is continuously moving across the CCD. The clever bit is they take the CCD, and as the stars drift, they shift the pixels down at exactly the same speed. So a star is always hitting a pixel, and the image data is building up as it shuffles down. Once it eventually reaches the edge of the CCD, then the data is read out, and when they find something, they say, right, there's a star. They make a note of the time at which that star hit the edge of the CCD. So Gaia doesn't save images. Gaia saves a huge numbers of timings. It basically has an onboard atomic clock, and it records when does this star hit the edge, when does that star hit the edge, etc., etc. We'll see a little animation of how it works in practice. But the bottom line is it doesn't store images, it stores times, which is a lot more efficient in terms of getting all of this data back to Earth. Two telescopes, one detector. This idea of we are going to send information from both telescopes to the same sensor at the same time, at first seems quite counterintuitive. But actually, that's how sextants work. If you want to measure the height of a star above the horizon, you take your sextant, and because there's a couple of mirrors in place, you can point it at the horizon, and the horizon comes through the telescope to your eye, and at the same time, a star at a different part of the sky bounces off the mirrors, and hence that star then appears to be on your horizon. So you are actually measuring that angle by placing the star on the horizon and using the scale at the bottom to tell you how high is the star relative to your horizon. That's how you use it. That's how you get your latitude, by measuring that angle. So in a sense, a sextant is taking light from two objects, the horizon and the star, and is putting them together in the same detector, which in this case is your eye. And so you get two images on the same detector, but that gives you the precision of being able to measure that angle. Even if the ship is rocking backwards and forwards, you don't have to worry about the star going up and down and the horizon going up and down, because they are both placed in the same field of view. And that's what the Gaia optical system does. It has two telescopes with two primary mirrors here, each of them more than a meter or so across. And there's the technicians at Astrium actually working on the Gaia optical bench with those mirrors. Gives you an idea of scale. The arrangement of CCDs in the array is quite interesting in itself. It has a whole batch which are responsible for timing the times at which star drifts across each of these CCDs. Each of them is about 5 by 6 centimeters, and the individual pixels are not square because it's the precision with which the stars are moving across the CCD that is important. There's a couple of sets of CCDs which are responsible for figuring out, did this star come from telescope 1 or did this star come from telescope 2? There's also CCDs for measuring how bright is it in the blue and the red, and also there are CCDs for taking spectra as well. So we get color information and brightness information and spectral information, as well as where are the stars in the sky. There are other chips which are there for technical reasons to make sure Gaia operates. The stars drift in that direction. It takes about 4 seconds to move across a CCD, so it takes a star about a minute to cover the entire CCD array. So let's see that in practice. There's Gaia spinning. The colors here are just representative, so we can work out which is telescope 1 and which is telescope 2, colored for convenience here. So when we think about the light coming in one of these telescopes, the light hits one of the mirrors, it bounces all over the place because the focal length is actually about 35 meters folded up. And those stars then basically hit the main CCD array. Let's remind ourselves about the other telescope. So the other one is hitting the other mirror and ultimately hits the same detector. So those stars hit the same detector. As Gaia spins, it's mapping out 2 bits of sky, so it has to try and keep track of where these stars actually came from. As the star moves across a CCD, it waits until it gets to the end, reads it out, and it makes a note of the star brightness and the precise time that it finished that transit. It doesn't read the entire chip if it knows that only those pixels have got a star in them. So it doesn't bother wasting time. But as a star drifts across the entire array, it builds up a set of timings of when it hit each of the CCDs. It also records how blue was the star, how red was the star, and also takes it through a spectrometer so that it can ultimately calculate or record the spectrum of some of the stars as well, not necessarily all of them. So in practice, what's actually happening is it's trying to work out on the right, did this star come from telescope 1 or telescope 2? And then it tracks effectively every star as they go across the array. This cartoon is showing a few dozen stars. Bear in mind, in practice, there might be 1 million stars on the array at any given time, and it's reading out something like 3,000 stars every second. And it's doing this 24/7 for 10 years. 3,000 positions are noted every second, and each star is recorded multiple times as the telescope sweeps around, and because it's rotating in 6 hours, those stars will come around again. Not only will it record it for telescope 1, and then 2 hours later, the same star for telescope 2, it'll also 6 hours later do the same again. So it records the same star hundreds of times. So even though it's only giving it something like microsecond timing accuracy for each CCD, it's ending up with many hundreds of measurements, which of course means that the average speed at which a star is moving, and hence knowing how Gaia is spinning, the precise position of those stars in the sky can be determined very accurately. So Gaia spins once every 6 hours, and it is processing as it goes around, and therefore it actually maps out the sky as indicated by this map in the bottom right. It maps out a ribbon of sky and then slowly processes round such that it ultimately maps out the entire sky. It doesn't necessarily cover the same bit of sky the same number of times. Some regions happen to be covered more often than others. The colors here indicate how often a particular star is measured during the lifetime of the 5-year mission. All that really matters is every star is covered hundreds of times. Ultimately, you then end up with a map of where everything is in the sky. So what data was acquired? Well, the original mission was 5 years. It was then extended for another 5 years. And there have been various data releases. You might assume they're numbered 1 to 7, but no, they're numbered 1 to 5. The original data release covered the first year's data and gave you the coordinates of millions of stars. The second data release gave you 2 years of data, and because of the additional data, it then gave you the coordinates of billions of stars. People were getting antsy and waiting for data release 3. So before data release 3, they actually improved the precision by analyzing more data, in this case the first 3 years of data, to improve the precision with which the catalogues could be produced. And then eventually data release 3 came out in 2022, where in addition to high precision measurements of billions of stars, they also made catalogues of millions of variable stars, millions of galaxies, hundreds of millions of spectra, as well as accidentally finding loads of solar system objects because it's looking for anything that moves. So it actually found about 100,000 solar system objects. The following year or so, they refined the analysis for a number of different reasons. This was called a focused product release, as well as updating, because we've now got 5 years of data in the mix, as well as giving much higher precision for the billions of stars that it was covering. It also said, well, what are we going to get if we look at a particularly dense part of the sky? So for those of you not familiar, Omega Centauri is actually a star cluster which is very dense. So we know there are going to be data releases coming along. So for instance, data release 5 won't be until something like 2030. Data release 4 should be this year. But the idea of looking at a very crowded region like this particular globular cluster is that we know it's very difficult to work out, for instance, what is going on when the stars are so close together. No telescope has problems working out individual star positions, for instance, out here, but trying to work out how many stars are there in this cluster in total Even the Hubble Space Telescope can't resolve all the way to the core of a cluster like this. When Gaia looked at Omega Centauri, it found an additional 500,000 stars that weren't known about up to that point. In other words, 500,000 stars that Hubble had missed. They had to refine the algorithms for finding stars in really dense parts of the sky. They are going to use that for later data releases by looking at the center of the Milky Way, where again, we know it's really dense in the core of the Milky Way. They've refined the algorithms by practicing on Omega Centauri. They're then going to use those algorithms for looking at what's going on in the Milky Way itself. Just as an idea of where we sit in the Milky Way, that's us sitting in the Orion arm, what used to be called the Orion Spur, now called the Orion arm of the Milky Way. We are about 8 kiloparsecs, or if you prefer, 25 kilolight years away from the center. If we think about what Hipparchus told us, Hipparchus gave us information about stars inside that yellow dot. That gives you an idea of just, it was only our local neighborhood. Data release 2 of Gaia extended that to a larger chunk of the Milky Way. Data release 3 extended it enormously. So data release 3 has now given us information about stars inside that green circle. So we now have a much better sample of what's going on, not just in our immediate neighborhood, but in regions around the Milky Way. This isn't an image, this is simply a plot where each pixel's color is determined by how many stars are there in that pixel. So in other words, the bright region in the center there just means there's lots of stars there, out here relatively few. So it looks like an image, but really it's just a plot of all the positions determined by Gaia. So what can we learn from all this phenomenal data? Well, amongst other things, we get a much more accurate Hertzsprung-Russell diagram. Remember, that's luminosity and color. This is not a schematic, this is actual data. Each of these dots represents a star. Each of these pixels in here is colored according to how many stars have an entry in that particular bin of this map. So now this is not just a schematic of what we think luminosity versus color looks like for the Milky Way. We now have millions of data points that tell us this is the actual plot of what stars look like, and this helps us understand stellar evolution within the Milky Way. By accident, we've also found the fact that there were quite a few sun-like stars indicated here by the yellow dots that have unseen companions, which is the blue line. By simply noting how these stars move, this is not to do with the motion of the Earth, this is not to do with individual proper motion. Once you've taken those out, you're still left with the star that seems to be orbiting something else which we can't see. Unlikely to be a black hole, much more likely to be a neutron star. So we've actually found by accident loads of neutron stars simply by looking at what bright stars like our sun are actually doing. We've also come to the conclusion by looking at what stars are doing in terms of their positions, that the Milky Way is actually warped. It's actually not perfectly 2 fried eggs back to back, as seen sideways here. It's actually got a warped tail. Perhaps that shouldn't be so surprising, because when we look at other galaxies, if we look very closely, there's a dust lane down the middle of this particular galaxy, some millions of light years away. But perhaps you notice that the dust isn't quite down the middle there. It's actually warped in much the same way that our Milky Way is. So we suspected that was a possibility. Gaia has now given us the data to show that that is indeed the case. If we look at lots of nearby stars in the Milky Way, we can look at their motion and get an idea of dynamics. We can say not only where are the stars, but which way are they traveling. Here, predicting into the future which way they will travel over the sky, because of course we've only been watching them for 10 years or so. But by looking at the motion of stars, we've noticed that some of them seem to be behaving themselves, going around the Milky Way as we would expect. But some of them are in very odd orbits, so-called needle orbits. In other words, very eccentric, going around the core of the Milky Way and coming out, and going around the core of the Milky Way and coming out. A bit like some of the very eccentric orbits we see of asteroids in the solar system. But if stars are doing that in the Milky Way, that tells us something about the history of the Milky Way. Because if the Milky Way formed and simply has settled down over billions of years, you'd expect all the stars to be like the lanes of traffic in a motorway to be all going in the same direction and roughly parallel to each other. The fact that some stars appear to be in very odd orbits and some stars appear to be going around the Milky Way the wrong way, that tells us the Milky Way has collided with other galaxies in the past. So a very complex map of many millions of stars have given us information about Milky Way dynamics. We've always assumed that the Milky Way has cannibalized other galaxies in the past. We occasionally see that happening for other galaxies out in the universe. Now we've got a much better idea of what has actually happened in the past. Here's the Big Bang on the left, present day on the right. And we think various galaxies have interacted with the Milky Way. I'm not going to go through them all. The Enceladus galaxy, we think, collided with us about 10 billion years ago, and it actually brought some of the star clusters that we see to the Milky Way. Some of the star clusters we see in the Milky Way, we think were not born here. We think they were born in another galaxy, which then collided with us and effectively merged with the Milky Way, and then populated our Milky Way with some additional stars. The Sagittarius dwarf galaxy on the right-hand side there, that's open-ended simply because we think that interaction is actually still happening. How does that actually look? This is not a particular galaxy. This is just a generic what might happen when another galaxy interacts with the Milky Way. Well, it'll certainly distort the spiral arms for a little while, but eventually they will merge together depending on the speed at which they hit. And you notice that the population of the interloper galaxy isn't spread throughout the entire Milky Way. It tends to be clustered in particular regions. And so if we see the motion of stars in particular blobs of the Milky Way, we can infer that that must be the result of a merger with an earlier galaxy. So it's simulations like that, as well as the dynamics of the star motion, that tell us about what galaxies have done in the past. One of the more interesting ones is what the Sagittarius galaxy has done recently. We think it collided with the Milky Way some 6 billion years ago, produced a whole load of new stars. It carried on. It wasn't completely merged at the time. It carried on, and it had a second encounter with the Milky Way about 2 billion years ago. And then it continued on and had another encounter about 1 billion years ago. And what that galaxy looks like now is effectively, well, it's a mess. It's a stream of stars that has, if you like, the trail left behind by this galaxy, which has interacted with the Milky Way 3 times over the course of history. One of the interesting points about that particular encounter 6 billion years ago was that we know there was new star formation back at that particular point. And interestingly, that's when the sun was born. So it might be that the interaction of this particular galaxy, the merger, or at least the interaction of the Sagittarius galaxy with our Milky Way, that we know produced new stars. It might well be that our sun exists because it was prompted by that merger between the Sagittarius dwarf galaxy and our Milky Way. We can't easily prove that, but the timing is about right. And remember these star streams that we deduce exist if galaxies interact with the Milky Way? Well, we certainly see them in other galaxies. And therefore, there's, again, perhaps no surprise, this is evidence that there have been mergers with this particular galaxy, again, some millions of light years away. If the star streams don't show up very well, I can invert the image and change the contrast. So we see these streams which indicate a galaxy has come close and left behind a trail of stars as it interacted. And the more we look, the more we see. This galaxy looks relatively peaceful, but if we do the same and invert it and bump up the contrast, we see that there are these star streams. So the idea of galaxies merging is much more common than we thought it was decades ago. And when we see it in distant galaxies, we now have evidence from Gaia that it happened with us as well. There's another example where there's clearly a lot more stars outside the galaxy than we would expect. And in this case, a galaxy in the southern hemisphere. Again, it's not just 2 galaxies. There's a whole load of stars in between them, indicating that they have interacted with each other. The galaxy merger history, I've said on the right-hand side there, the Sagittarius dwarf galaxy started interacting with us 6 billion years ago, and that might be the origin of the sun. But it hasn't finished, because if we move that over and think about the future, 0 is now. But in the future, well, I'm sure the Sagittarius dwarf galaxy will continue interacting with us in some way or another. But we also know that there are 2 mergers that will be coming in the not so distant future. In about 2 to 3 billion years, we will be merging with the Large Magellanic Cloud, the satellite of our galaxy, which currently is just sitting down there in the southern hemisphere, minding its own business. Gaia is telling us that the movement of stars in that satellite galaxy is such that it will collide in 2 or 3 billion years. And as we possibly already know, we will be colliding with the Andromeda galaxy on a slightly longer timescale of about 5 billion years. We will probably be merging with the Andromeda galaxy. It's difficult to calculate whether it's going to be a head-on collision or a glancing blow, but we will end up merging with other galaxies. So let me finish with an epilogue. Gaia finished its work. Its 10-year mission was finished effectively in January 2025, which was around the time I decided, wouldn't it be a good idea to have a talk on Gaia? Its data was finished by about January, and in March it was put into a retirement orbit. Sounds so much better than a graveyard orbit, doesn't it? So a retirement orbit means if you're in orbit around L2, such as Gaia and the James Webb Space Telescope and other telescopes, all you have to do is nudge it a little bit beyond L2, and once it's nudged beyond L2, it basically just goes around the sun, but not in sync with the Earth. So it doesn't then stay close to L2. It drifts away, but it will continue orbiting the sun. It's being pushed into an orbit which won't get it close to any other telescopes for the next century or two. But because it's going around the sun, it will actually come close to the Earth again at some point. Probably about 14 years from now, it will come close enough to Earth to be perhaps visible. As it drifted away from L2, it was actually visible from Earth. This little S you can see in the middle of that image, that's an amateur taking a picture of the sky, and there's Gaia drifting away from L2 as it was put into its retirement orbit. The last message sent back from Gaia, the ground controllers deliberately gave it some dummy data, which then got transmitted back and color-coded so that it actually produced "bye" as its last transmission. It deliberately gave it numbers. Normally those numbers are highlighted if they're good or bad. In this case, they gave it deliberately bad data to highlight that particular message. Gaia doesn't have a replacement as such. Some space telescopes, for instance, imminent, perhaps next year, the Nancy Grace Roman Space Telescope will be launched. It's not a replacement for Gaia, but it will do some complementary work in the sense that the Nancy Grace Roman has got very high resolution. It's got the same resolution as the Hubble. This is the field of view of the Nancy Grace Roman, and right in the middle there, that's the field of view of Hubble. They have the same resolution. So imagine all of the fantastic images that Hubble has produced, and then imagine an image that is essentially 100 times bigger than that. Nancy Grace Roman will be fantastic. It will be able to produce astrometry, in other words, the measurement of star positions very accurately. It hasn't got time to cover the whole sky. Much like the Hubble, it will be producing some very accurate measurements to complement the Gaia data set, but it hasn't got time to do that much. Gaia doesn't produce understanding. Gaia produces data. The next data release will be about 500 terabytes of data about stars, their positions, their motions, their colors, their spectra. What we do with that data, well, that's a question of a lot of people thinking about, yeah, okay, we've got human brains, perhaps assisted by AI tools, to go through that 500 terabytes of data and ask, what is it actually telling us? The reason we took that data is to give us star motions so we get Milky Way dynamics. So we're already getting better understanding of how the Milky Way moves, how it formed, how it's dynamically changing, how it's evolved, how it's merged with galaxies in the past. But There's more data to come. Data release 4 will be far more data than the next. Data release 5 doesn't come along until 2030 and will be the full 10 years of data, which will give us much more information about Milky Way dynamics and possibly tell us about other galaxies merging with the Milky Way. Remember, we're also getting color information and spectral information, which means we have now billions of stars, and we can now judge whether or not our models of stellar evolution are as good as we thought they were based on all this data. And almost by accident, we're also getting information about neutron stars and black holes. The solar system, we're finding exoplanets as well. Gaia actually found one of the biggest black holes in the galaxy, other than the one at the center, almost by accident, by looking at how stars were behaving. And when we take the entirety of the data set, it is thought that we'll learn a lot more also about dark matter and dark energy. So the understanding comes from what are we going to do with this shed load of data? We've already been using it, and we have to remember that the catalogues that Gaia has produced will be standard catalogues for the next 10, 20, 30 years. It's not anticipated that any telescope is going to come along until at least the 2040s, possibly the 2050s. No telescope is going to come along and improve on the Gaia data set. So we've got plenty of time to think about what to do with this data, and it's going to be a mainstay of catalogues for ground-based telescopes as well as space-based telescopes for decades and decades to come. Thank you very much for listening.